All right, back here talking to you about factor analysis again. This is the third part in a four-part series on factor analysis. Today we'll talk about exploratory factor analysis, components, factors, and rotations. If you haven't viewed parts 1 and 2, you'd probably want to go back and watch those before you watch these, as I refer to a lot of the concepts that I talked about in the earlier slides. We're going to start off by doing a components analysis. Remember, components analyses are analyses where we're reducing the number of dimensions we have in a data set. And by dimensions, I mean the number of variables we have. We have a data set, for example, here with 9 variables, so it'd be 9 dimensions. We try to reduce that to a smaller number of dimensions while taking that allow us to group variables that kind of go together, variables that are more strongly correlated with each other than with the other variables, to create kind of sets of variables, or what are called components in this case. Remember, I don't recommend component analysis, although it is very popular. It does demonstrate nicely some of the statistics we're working with. The reason why I don't like components analysis is that components analysis tries to explain all of the variability in all of the variables. That includes variability that's shared between the variables. You can think of that as the pieces of the variables that are correlated with each other, but it also includes what's not shared among any variables, or what would be more commonly called error variance. The reason why I don't recommend components analysis is that because it includes that error variance, it often produces results that are unstable because it's based on this random noise in places. In contrast, factor analysis just focuses on the common variance. Remember, with factor analysis, we're looking to group variables together. So to me, it makes a lot of sense to focus on that common variability, because that's really what we're looking for, and that's going to be more stable. I'm going to do a couple of things here that we wouldn't normally do in analyzing data, more to just demonstrate some of the statistics we're working with. We're going to start with a solution where we have the number of factors, or the number of components, equal to the number of variables that we have. So I'm going to extract 9 components and to explain 9 variables. Again, that's just to demonstrate a couple of statistical values that we're talking about, and then we'll move on to an analysis with 3 components. That's not what parallel analysis suggested would be right here when we talked about number of factors, but it will allow us to compare results across component analysis and factor analysis. All right, here, the code that we use is simply the code principal. The name of the data file, or technically this is a correlation matrix, is Thurston. Even though these are components, we have to give the command n factors equals 2. You can see how, I mentioned in the first slide, people often talk about factors and components interchangeably. Rotate is equal to none. We'll just leave that aside for now and then come back and talk about the importance of rotation later. And then this FA sort command, this is a nice command for helping us to interpret our factor loadings, which we'll do in a little bit. So in running this analysis, we can see our variables are listed on the left, vocabulary, sentences, sentence completion, and so on. And then across the top, it has the 9 different components that are represented, and those numbers in there are the factor loadings. So we can see for 9 times 9 variables and 9 components, so we're going to get 81 different values represented there. We're not going to interpret those at this point. Those will be the values that we use to interpret what variables go with what in a little bit. But for now, the only statistic I want to draw your attention to is H2. H2 is what's called the communality, and that's how well any individual variable is explained by your components or factors. H2 here for each of them is 1, meaning that they're fully explained. This goes from 0 to 1. You can think of it like an R-square value, getting at how well each of those variables is predicted by these 9 factors. So these are all 1, and that tells us something about component analysis. 1, it's trying to explain all the variability, and it will explain all of the variability. It'll explain 100% with 9 components. We actually want to reduce the number of dimensions we have, though. We don't want to go from 9 variables to 9 components. It doesn't help us at all in terms of grouping these variables. So what we're going to look for is the optimal solution in terms of how many components we can use and still get a reasonable amount of explanation of each of these variables. So 9 will always give you 100%, but that's not really useful in reducing the number of dimensions that we're dealing with. Other pieces that we get here, we get the sum of squared loadings, which are called eigenvalues. This has to do with these get at how much each individual component is explaining. And those values will range from 0 to however many variables you have. So these can range from 0 to 9. And to kind of evaluate the size of these, you can look at the proportion of variance. That's simply the eigenvalue, the sum of squared loading, or the eigenvalue, divided by the number of variables. So you can see for the first one, it's 0.54, 4.85 over 9, again, 9 being the number of variables, is about 54% of the variance. One thing to also note, if you look at those eigenvalues, they always get smaller as we go down the list. First variable on the scene gets the most explanation, and then the rest are left to pick up whatever's remaining. Another valuable piece here is cumulative variance. That's how well we're explaining the variability in our variables in total, and you can see this goes up. 0.54, it goes to 0.66. That's just each proportion plus each proportion. You can think of the cumulative variance almost as an R square for the entire model. So if we ran a model with just PC1, it'd have an R square of 0.54. With PC2 added in as a second predictor, it'd have an R square of 0.66. And then you can see the proportional variance, that's like the R squared change, how much we're increasing our explanation. Note that the cumulative amount explained here is 1.0 or 100%. And again, that's because we haven't actually reduced to fewer dimensions. The fewer dimensions we use, the fewer components, or with factor analysis, the fewer factors, the less variance we're going to explain, but we want to get the optimal trade-off. Reasonable number of dimensions that allow us to group our variables in meaningful ways versus explaining 100% of the variance, which isn't really necessary. All right, here I've done the analysis and limited to 3 factors. You can see the code is the same, except the n factors command changes. And when the n factors command is put at 3, we can see that we get now just across the top PC1, PC2, PC3, principal component 1, 2, and 3. So we only have 3 of those to deal with. The communality, remember the communality is H2, very confusing that there's a column called com, which is not the communality. So communality H2, you can see that we now have smaller values, but not substantially smaller. We're explaining 86% of the variance in vocabulary, 86% in sentences, 83% in sentence completion. Pedigrees is relatively low comparatively at 0.67, but these are all still pretty well explained. And then if you look to the sum of squared loadings, the eigenvalues, you can see we kind of cut off after the, we only have 3 now, but the cumulative variance explained is still 0.78. So we're explaining over 3/4 of the variability in these 9 variables with just 3 components. So 3 going from 9 dimensions to 3 dimensions gives us a nice balance between having a reasonable number of items. We don't know yet if that's an interpretable amount. We'll see that when we get to rotations, but we have kind of traded explaining everything versus having fewer dimensions, having these groupings and explaining a bit less. All right, at this point, I'd like everybody to go to examples 2 and 3. In example 2, you'll be running a couple of component analyses. I asked you to do it with 3 variables and 9 variables just to get a sense of that. And then in example 3, I asked you to explore the communalities and the sums of squared loadings, or the eigenvalues. One thing we can see is with the communalities, if we square each factor loading going across. So what I have here is is an example where we're squaring the values for the first variable, which I thought was vocabulary. Oops. got you exploring those values, squaring them going across, squaring them going down. We can see if we square the values and add them going across, we get the eigenvalue. If we square them and add them going down, we get, I'm sorry, if we square them and if we square them going across, we get the communality rather. If we square them and then sum them going down, we get the eigenvalue. So there's some examples there. To explore those concepts, I encourage you to certainly work through those examples and see what you get. All right, so I want you to pause here, go over to R, and run those examples. All right, we're back after you've gone through and done that example. Now we're going to go to doing factor analysis, or what's called PAF, principal axis factoring, a very common version of factor analysis. Lots of different approaches here. The psych package defaults to something called MinRes, or minimum residuals. Different people like different analyses in general. There's not going to be a ton of difference between the different approaches that would be noticeable to anybody except somebody who works developing factor analysis. Again, the biggest difference between factors and components is that components use all the variance, factors only use the shared variance. Generally, most sources would recommend factor approaches over component approaches. Researchers still use component approaches a good bit, and I think part of that is because its results look more impressive numerically, because there's more variance to explain. Although it's probably not as stable because of its reliance on unshared variance. So factor analysis, definitely the recommended method. I think that really the only reason why people did one over the other more commonly is historical. It was probably easier to do components analyses by hand, so that's what people saw in the literature, and then that proliferated. Again, factor analysis is probably the way to go here. The command for factor analysis is simply FA. Here in this example, we have to give it the number of observations because we're using not raw data, but a correlation matrix. FM equals PA gives us the principal axis approach, and then rotate none. Again, just leave that aside for now, and we'll get to that in a minute. We can see here some differences. The eigenvalues and the communalities are going to be a bit smaller. In comparing the cumulative variance explained, we explained 67% here using factors, but only 78% for components. Keeping in mind that that extra 9% there, that was variance that was basically error variance. It wasn't shared among any variables. So it's kind of just noise getting bumped into our solution. The communality numbers are going to be smaller across the board. I think it was 0.86 for the first two of them for the component analysis, but it's 0.84 and 0.82 here. So you can see we're going to get smaller numbers. Generally, we'll get a result that's consistent with the components analysis, but the statistical values aren't as big, so maybe less impressive in some ways. All right, other things to do here. At this point, I'd like you to complete example 4 and exercise 2. Example 4 basically has you run both types of analyses and compare them, noting the differences between the eigenvalues, communalities, and various other pieces. And then exercise number 2 has you use a data set that's included in the psych package called Harman-Holzinger, do a parallel analysis, and you used this earlier to do a parallel analysis. Here you're going to be extracting the number of factors suggested by that analysis. You could try that with components as well if you like, but for extra practice. All right, so pause the video and we'll be back in a second. All right, and we're back. Up to this point, we haven't talked about the factor loadings very much. The reason for that is that the factor loadings are largely useless unless we have done what's called factor rotation. Factor rotation is an approach that will help with interpretability. I would say you almost always want to rotate your factors, but then I would scale back and say there's some applications where we don't initially rotate, such as intelligence research on G factor, like general intelligence. That's a solution where we have one overarching factor and then try to explain variance, that is explained by the remaining factors after we remove that general factor. For our purposes, we're going to be rotating. Sorry, I've got visitors here. For our purposes, we're going to rotate, as that's the most common approach. There would only be special applications where you wouldn't rotate. And what we're going to interpret post-rotation are the patterns of the loadings. And the goal here is going to be determining what variables go with each factor. And then possibly we could even give the factors names to represent the overarching construct that they represent. So in terms of rotation approaches, there's two general approaches. There's orthogonal approaches and oblique approaches. Orthogonal means that our factors are forced to be uncorrelated. Varimax rotation is a very popular version of this. There's other versions of it as well. And then there's oblique rotations. With oblique rotations, our factors are actually correlated. Oblomin is one very common approach here. Again, the specific approaches that I use, maybe not everybody uses them. You'll see some variability here. Really, any of the approaches are all interpreted in the same way. So if you're working in an area where there's another approach that's more commonly used, go ahead and use that, and you'll see that the interpretation is the same. It's not going to be any different to interpret min-res or Equimax or anything like that. I'm sorry, min-res isn't a rotation. In general, I would say that orthogonal rotations are most common. And again, I think that's something that's probably historical in that they're easier to calculate if you have to calculate them by hand. Oblique rotations are more realistic. They're sometimes a little messier. And again, we know, psychology as a field has problems with messy results. So even though oblique is more realistic, sometimes people avoid it. Keep in mind that oblique means the factors are correlated. If you have 9 items measuring some form of, say, intelligence, you would expect there to be some correlation between the factors that are represented there. You wouldn't expect them to be completely independent. So probably a more realistic situation. I know that a lot of recent work has recommended that we should focus on oblique rather than orthogonal rotations, although the literature tends to skew toward orthogonal. In running the orthogonal rotation, we have basically the same code, but where it used to say rotate equals none, now it says rotate equals varimax. And there's a whole host of different approaches available in the psych package that you can read up on for different rotations. Very easy to implement them. You just need to know what the name is. The main key with rotation, one thing I want to note here is the communality values stay exactly the same. So we don't have any change in what's explained in any one variable. The eigenvalues change, but cumulatively they stay the same. We can see here we still have that 0.67 value for the cumulative var. That's how much is explained in total. That doesn't change. So nothing changes about how much variability is explained or in any one variable or overall. What does change is how it's parsed out among the different factors. And if we look at the eigenvalues here, we can see that now these eigenvalues, it used to be that 1 was really big and 2 and 3 were even below 1. Now what we see is that it's spread out a lot more evenly. And that's what rotating the factors will tend to do. It'll spread things out a little bit more evenly. Ideally, what it will do is it will isolate certain variables on specific factors while minimizing their relationship with other factors. What having these rotated loadings do is it allows us to interpret the factors in a little bit more meaningful way. If you look at, for example, the first factor, PA1. You can see we've got large loadings for sentences, vocabulary, and sentence completion, and then comparatively smaller values for the remaining 6 items. So when we move to factor 2, we can see we have small loadings of 0.2, 0.32, 0.28 for the first 3 variables, and then for the next 3, we have relatively high loadings, all of them over 0.6. And then when we get to the last 3, we see we have smaller loadings of 0.18, 0.31, 0.17 for PA2. For the third factor, we see that it's the last 3 variables that have the highest loadings, and it's relatively small values and small loadings on all of the others. So what this is really doing is it's taking our variables and it's putting them together in, it's trying to isolate them on certain factors. Interestingly, the FA sort command, that sorts these variables, so they're in a different order than they would have been in the data set. It sorts them in terms of those sizes, so you can get a kind of a visual of this. You can see the first factor has sentences, vocabulary, sentence completion, something about sentences and words, their word meanings. The second one, first letters, 4-letter words, test dealing with suffixes. So this is dealing with smaller chunks. So, and then finally, the last one, letter series, groups, pedigree, that is origin of words. This has something more to do with categorizing different words. So we have a factor that's related to something about large chunks of sentences, something that's related to small chunks, which is the letters. And then finally, these series, groups, pedigree, these are kind of patterns that are being represented. So we're getting like with like there. Just to highlight differences between different rotation techniques, here are the correlations between the factors, and you can see that the factors are forced to be correlated, to be uncorrelated. Those 1s are their correlation with themselves. The 0s are their correlations with the other factors. And you can see that they're all 0 here, meaning that there's no correlation between the factors. They're not allowed to correlate at all. There may be some cases where that's realistic, but and we'll examine whether that's really reasonable for these data in a second. All right, at this point, I'd like you to explore a little bit more about rotated and unrotated factors. So I've got an example number 5 here, which has you run these analyses with rotation, without rotation, and then ask you a few questions about the different different statistics. So pause the video and take a second to complete that. All right, going on to an oblique rotation. Very much the same code, except under rotate, I use the command oblimin. That's a specific rotation technique that's very common. Again, there's others. The interpretations of them does not differ across different techniques. So if you're in an area, again, if you're in an area that uses some other technique, it's fine. You're going to get the same sort of output and the same opportunities for interpretation. We can see oblique rotations, they also do not change the amount of variance that's explained. They don't change the communality. They just change how stuff is, parses out onto different factors. We again see basically the same pattern. Sentences, vocabulary, sentence completion load strongly on the first factor. And the first factor doesn't really have another strong one except for maybe pedigree down below. For the second factor, we have, again, the letters and suffixes. And then the third factor remains those things with groupings, and patterns, letter series, letter group, pedigree. Very much the same pattern here. The main difference being when we take a look at our factor correlations. These factors actually turn out to be pretty strongly correlated at the 0.5 range for all of them. those relationships really would have been ignored if we had used the more common orthogonal approaches. So another good argument for using an oblique rotation. At minimum, if you don't know what you're looking at, I would try it both orthogonally and obliquely. If you have very weak correlations using oblique, then it's reasonable to use orthogonal. But here we can see our factors are really strongly related and should definitely be examined using an oblique method. All right, example 6 and exercise 3 focus on doing factor rotations. Here I have you do an oblique rotation to test stuff out and then ask you to run and interpret a rotated analysis of the holes in your data, which we've been working with. And then see if you can identify which variables go with which factors. All right, the next video will cover confirmatory factor analysis and introduce structural equation modeling as an extension of confirmatory factor analysis. Again, the factor analysis handout on Canvas is lengthy and provides a different detailed example for more information. I definitely recommend you reading through that as well. And something I saw the other day, if you're still struggling with some of the R basics or just want more practice with R, there's a new package called Advent R, and you can read about that package and how to download it. I don't believe it's on CRAN, but there's instructions for installing this at the website here. It's written by Andy Field, who has written several really good textbooks on both statistics with various statistical programs. He wrote this to accompany his Adventure in Statistics text, which is really quite funny and good. It's very interactive. It's got topics covered, a place to run R code. Really, really a nice resource. Relevant to this class, in addition to the basics that we go over. It doesn't cover much with regression, but it does cover logistic regression, which will be the topic of which will be another topic that we cover in a couple of weeks. All right, everybody, I will stop here and see you in Factor Analysis 4.